Solar PV plant losses. A solar photovoltaic PV plant, despite being one of the most promising and clean sources of renewable energy in the world, faces multiple categories of losses that reduce its overall performance, efficiency, and energy yield and understanding. These losses in depth is essential for engineers, researchers, policymakers, and investors who want to optimize the return on investment and long-term sustainability of solar projects. These losses can broadly be classified into irradiance-related losses, optical losses, electrical conversion losses, thermal losses, mismatch losses, shading losses, wiring and cabling losses, inverter losses, degradation losses, maintenance and operational issues, and external or environmental factors such as dust, pollution, and weather variability, each of which contributes cumulatively to the gap between the theoretical maximum output of a PV system, called the nameplate capacity or STC-based rating, and its actual delivered energy at the point of interconnection to the grid. So to begin with, the first category of loss comes from irradiance availability and variability, because solar panels depend directly on sunlight, which is never constant, due to geographic location, latitude, tilt angle, season, and time of the day. The incident solar radiation varies continuously, and even at the best solar sites, daily and seasonal variations lead to reduced energy yield compared to the maximum possible, while cloud cover, atmospheric aerosols, dust storms, and climatic conditions further attenuate the solar radiation reaching the panel's surface. Which is why irradiance loss is considered a primary factor. Moving on to optical losses, these occur at the surface of the PV module due to reflection of sunlight from the glass cover, absorption in protective layers, or non-ideal anti-reflective coatings, which typically account for 2 to 6% energy reduction. And while modern panels use advanced coatings to minimize reflection, some percentage of light is inevitably lost before it even reaches the solar cells. After optical losses, electrical conversion losses within the solar cells themselves are critical, because the Shock-Lukwiser limit defines the theoretical maximum efficiency of single-junction silicon solar cells at around 33%, but commercially available modules usually have 17 to 22% efficiency, meaning a huge portion of absorbed solar energy is lost as heat or unusable photon energy. For example, photons with energy less than the band gap pass through, while higher energy photons lose the excess as heat during electron excitation, which explains why solar cells cannot convert all incident light into usable electricity. Then comes thermal loss, since PV cells are semiconductor devices and their efficiency decreases with temperature rise, typically around 0.4 to 0.5% per C, above the standard test condition of 25 degrees Celsius, meaning that in hot climate, panels can lose up to 15 to 20% of their rated power output. And this is why proper ventilation, mounting design, and in some cases active cooling mechanisms are critical in large-scale plants. Mismatch losses are another important category, arising because no two solar cells or panels are perfectly identical, and even small differences in current voltage for characteristics can cause energy losses when they are connected in series or parallel. While partial shading on one panel can disproportionately reduce the output of the entire string, unless bypass diodes or power optimizers are used. Shading losses deserve special mention, as shadows from nearby trees, buildings, poles, or even from other rows of solar panels, roturo shading in utility-scale plants, can drastically reduce generation, and in many cases shading of just 5 to 10% of a module can lead to a 30 to 40% reduction in output due to the electrical interconnection of cells. Wiring and cabling losses, though seemingly small, also play a significant role in large plants, because long runs of DC and AC cables introduce resistive IYR losses, which are typically around 1 to 3% of total energy. And poor quality connectors or improper cable sizing can further increase these losses, making careful electrical design and periodic inspection necessary. Inverter losses, another major contributor, occur during DC to AC conversion, as inverters have typical efficiencies of 96 to 98%, meaning 2 to 4% of energy is lost in the process. While additional losses may occur due to inverter clipping when DC input exceeds inverter capacity during peak sunlight hours, and these need to be optimized based on system design. System downtime and operational losses also reduce energy yield, since any malfunction, grid outage, or scheduled maintenance period results in lost generation, and though modern plants are designed for high uptime, even a 1 to 2% downtime per year can translate to significant financial loss. Degradation losses over time are unavoidable, as PV modules degrade at around 0.5 to 0.8% per year, which means after 25 years of operation, a module may only deliver 80 to 85% of its original rated capacity, while in harsh climates with high UV exposure, dust, or extreme temperature fluctuations, the degradation rate may be even higher, reducing the plant's lifetime yield. Dust and soiling losses are especially critical in desert regions, where accumulation of dust, sand, or bird droppings on the panel surface can block sunlight, leading to 5 to 30% output loss. If cleaning is not performed regularly, which is why water-based cleaning, robotic cleaners, or anti-soiling coatings are increasingly being used, snow cover in colder climates also leads to temporary energy losses until the snow melts or is cleared, while pollution in urban areas can deposit particulate matter on panels, causing chronic reduction in performance. Other environmental factors include wind, humidity, and hail, which can physically stress or damage panels and reduce efficiency, while storm-related outages or damage can create unplanned downtime. Transformer and auxiliary losses are also present in utility-scale solar plants. Since power must often be stepped up using transformers before transmission, and each stage introduces around 1 to 2% loss. While auxiliary systems like trackers, monitoring devices, cooling fans, or lighting consume a small but continuous fraction of generated power, reducing the net output delivered to the grid. In plants using solar trackers, though tracking increases irradiance capture by 10 to 25%, mechanical inefficiencies, misalignment, or tracker downtime can introduce additional operational losses. From a financial and system perspective, curtailment losses occur when the grid operator instructs the plant to reduce output due to grid congestion or low demand, which does not reflect the plant's technical inefficiency but still reduces the actual sold energy. Furthermore, uncertainties in forecasting solar generation can lead to penalties in some electricity markets, indirectly contributing to financial losses. In addition, aging inverters, degradation of cabling insulation, corrosion of connectors, and other wear and tear mechanisms gradually increase system losses over time unless preventive maintenance is performed. When looking at cumulative effect, a typical large solar PV plant may lose around 20 to 35% of its theoretical maximum energy due to the combined impact of all these losses, with major contributors being temperature effects, inverter conversion losses, mismatch and shading, and soiling. Therefore, modern solar engineering focuses on minimizing these losses through advanced module technologies like bifacial panels, passivated emitter rear cells, PERC heterojunction cells, and tandem cells that reduce thermal and spectral losses. Smart inverters with higher efficiency and grid support functions, string level or module level power electronics to reduce mismatch losses, robotic or water-efficient cleaning systems to minimize soiling. Improved plant design with proper tilt and row spacing to avoid self-shading, predictive maintenance to reduce downtime, and sophisticated monitoring platforms that allow real-time loss detection and corrective action. In conclusion, while solar PV technology has matured significantly and costs have dropped dramatically in the last 2 decades, the inherent and external losses associated with solar plants remain a crucial area of research and optimization. Because reducing even a small fraction of these losses can lead to massive improvements in lifetime energy yield and financial return, especially when projects are scaled to hundreds of megawatts, making the understanding and mitigation of PV plant losses a cornerstone of the global renewable energy transition.